All right, welcome back again, everybody. Um, Today we're going to be doing section 14.7, which is where we talk all about maximum and minimum values. All right. This one might be a little bit long because if you remember anything from Calc 1 about like maxes and mins and optimization problems and that kind of thing, that's all right here, or at least part of it's right here. And then we'll kind of do the same thing in the next section, which is on Lagrange multipliers and the Lagrangian. So let me get the slides pulled up and let's get started. Okay, so here's the overview. We're going to talk a little bit about the motivation for this. We'll define and locate local maxima and minima. We will talk about critical points. We're going to introduce this object that's called the Hessian matrix, or just the Hessian for short. And then that will lead us to what's called the second derivatives test. That's going to help us determine if a critical point is a maximum or a minimum or a saddle point. Then we will do at least one example of an optimization problem. Then we're going to introduce a couple of topological definitions from point set topology. We'll talk about compactness briefly, and then we'll get the extreme value theorem, basically a generalization of the extreme value theorem that you remember from Calculus 1. Then we'll finish up by talking about absolute maxima and minima and call it a day after that. All right? Okay, so here's the motivation. So just like we were using tangent lines and derivatives back in Calc 1 to find maxima and minima of one variable functions, we're going to do the same thing now in Calc 3 to find maxes and mins of multivariable functions. So the rough idea is that, we had tangent lines, then now we have tangent planes, and then in general you just have tangent hyperplanes. So these particular lines and planes are very important when it comes to optimization. And realistically speaking, a lot of what many of you are going to use this mathematical knowledge for is optimization problems. Basically, how do you get something to be the best or the worst or the biggest or the smallest? Optimization problems, that's a lot of what we use calculus for. Yeah, there you go. There are myriad applications of these techniques since they're just the basic tools of optimization problems. So, and you'll see in this lecture, this is one of the reasons why I like to emphasize conceptual understanding of these things, because it is the theory that is important for humans, because the actual process of performing the optimization itself can be very time consuming and very tedious and very technical. And that's really what we have computers for. So just bear that in mind, okay? And you'll see an example of that at the end of this set of slides. So let's first talk about local minima and maxima. Here's the definition. A function of two variables has a local maximum at a point A, B if the value of f at that point is greater than or equal to the value of f when you're near the point A, B. So let me explain what near is in just a second here. What we're really saying is it agrees with your intuition. A point is a maximum if a local maximum if everywhere around that point the value of the function is less, right? So the maximum is basically the top. It's the top point. Now, what we do is we say that you have to look near the point a comma b. And what we mean by near is literally for all points in an open disk centered at the point a comma b. So that's what we mean by near. Like if you were to draw a tiny little disk here, like maybe okay, like if this is a maximum right here, do this right here, and then you look down at this point, this would be the point a comma b, sorry, comma b, ah, comma 0, right? If you can make a little open disk around that point, and you look at all the values of the function at those points in the disk, and the values of the function are all less than the value of the function at the point a comma b itself, then that means this has to be a maximum. That's what it means. So your intuition is right. And the number itself, so the number f of a comma b, remember that's the output, that is the local maximum value. So when you hear the word local maximum value, they mean the output of the function at that point, a comma b. Similarly, kind of like in the other direction, if f of a comma b is less than or equal to the values of f when you're near a comma b, then that means that f has a local minimum. So intuitively speaking, if if this point is below all the other points, then it must be a local minimum, right? And then f of a comma b is what we call the local minimum value. So here's a nice picture, a nice diagram from the book. We haven't talked about the absolute maxes and mins yet. We'll talk about those at the end, but this is a local maximum and this is a local minimum. So it really does agree with your intuition. If you've got a little like peak right there on your mountain range, that's a local maximum. Now, that doesn't mean that that peak is the highest peak in the entire mountain range, right? That the highest peak in the entire range or the entire mountain area, that would be the absolute maximum. That's the highest peak. And then conversely, this right here is what's a local maximum. It's basically a little trough, right? It's like a low point, but that doesn't mean it's the lowest point. It's, you can have a deep part of the ocean, but that doesn't mean it's the deepest part of the ocean. The deepest part of the entire ocean, that would be the absolute minimum. So that's the distinction between local and absolute. Sometimes I will use the word global instead of absolute just to mean like, everywhere instead of locally. So if I say global, I mean absolute. Okay, so here we're going to start with this theorem. So if f has a local max or a min at the point a comma b, and the first order partial derivatives of f exist at that point, then f sub x must be 0 and f sub y must be 0, right? So geometrically what this is saying is if your function has a local max or a min and the partial derivatives exist, then the tangent plane has to be horizontal. That's what it's saying. So this agrees with what you saw back in Calc 1 when it was like, hey, if you have a maximum or a minimum, then it must be the case that the slope of the tangent line is 0, right? That's what this is saying, but now it's saying it for functions of 2 variables, right? Same idea. Now, wait, do I say it here? Oh, not yet. Let's prove it real quick. So this is a common technique of proving things in multivariable calculus. You basically fix your other coordinates and look at everything with respect to one variable. So let g of x equal f of x comma b. So we're fixing y to be equal to b. Now, if f has a local maximum or a minimum at a comma b, then that means that g must have a local maximum or a minimum at x equals a. So by Fermat's theorem, which is the theorem that you get back in Calc 1, section 3.1 from this book, we know that the derivative of g at a has to be 0. But the derivative of g at a, by definition, is equal to the partial of f with respect to x at a comma b. And so that means that since this is 0, this has to be 0 too. Similarly, if you apply Fermat's theorem again to this function, where you basically fix x instead and let y vary, then you get that the partial with respect to y is also going to be 0. That's the idea. So if you have a local maximum or a minimum and your partial derivatives exist there, then they must be equal to 0, guaranteed. Okay, so now we can define what a critical point is. So a critical point of a function, we'll say it's the point a comma b. So a comma b is a critical point if the partial with respect to x is 0 and the partial with respect to y is 0, or if one of those doesn't exist. So that's what a critical point is. So just to reiterate, to have a critical point of a 2-variable function, both of your partials have to be 0. So they have to exist, and they have to both be 0. Or one of them has to not exist. That's another case of a critical point. Right. Now, this is one of those times where it's very easy to mix up the direction of implication here. And that's one of the reasons I've been kind of emphasizing things with the way that I say them. So it's this note right here. Just because a function has a critical point somewhere, that doesn't mean that it has to be a maximum or a minimum. All right, so beware of that. Just because you have a critical point, that does not mean that it is a peak or the top of a peak or the bottom of a trough. So beware of that. That's not what it's saying. The direction's the other way. Theorem 1 says if a function has a local min or a max, then the partial derivatives must be 0. So the direction is the other way than you might wish, right? This is not saying if the derivatives are 0, then you have a max or a min. It's saying if you have a max or a min, then the derivatives are 0. So it's different. Yeah, the converse can be false. Okay. All right, so this one, let me see. Do I want you to try to do this one on your own? Mm, Here, yeah, try to start this one on your own, and then we can work through it together if you don't get too far, no worries. So find the extreme values of this function. So basically, find the critical points and find if they're maxes or mins or not, all right? Think about how you would start, right? And then say something out loud to your friend, your group mates, your dog, your cat, your hamster, just something, or just to yourself to give your brain that audio feedback. Okay, now try to work it out on your own, and we'll do it together in just a moment. Okay, here we go. So if we're finding extreme values, a good place to start is to take the partial derivatives. So we're going to start with that. Partial derivative with respect to x gives us this. Partial derivative with respect to y gives us this. And now we're going to set those partial derivatives equal to 0 and solve for the input variables. So this is equal to 0 when x equals 1. And this is equal to 0 when y equals 3. So we know that there is a critical point at 1 comma 3. Also, I'll point out that both of these functions are polynomials. They're actually linear. So they're defined everywhere. There is no place where they won't exist. So there you go. The only critical point we have now is at 1 comma 3. Now the question is it a maximum? Is it a minimum? Is it neither? What's going on at this point? It's a critical point, but we want to know what's going on. So yeah, what we would need to do is we'd need to know if the value of the function f at points near 1 comma 3 are greater than or less than 4, right? So we could plug in some values near that point to get a good guess, but the issue with that is that's not sufficient. So beware, you can't just like test a couple of points and be like, oh look, it's less than at that point, therefore it must be a maximum. You would have to test every possible point, which is impossible to do individually. So beware of that. So one thing we could do is we could determine if this is a minimum or a maximum by recognizing that this is actually the graph of an elliptic paraboloid. So this function here describes an elliptic paraboloid. The only difference between this and what we saw mostly in section 12.6 is this one is an elliptic paraboloid that's been shifted, so it's not at the origin. That's why you have these extra terms. Those terms encompass a shift in the x and the y directions. So if you take this and complete the square on x, take this and complete the square on y, you can rewrite this formula in its standard form, and now you can more easily see that it is indeed an elliptic paraboloid. That, plus that. Actually, is it even elliptical? It's a circular paraboloid. Yeah, circular paraboloid, because there's no scaling factor here. Yep, it's just been shifted up. So maybe I should change that. Not elliptic, but circular. There we go. All right, so this is one of those situations where knowing a little bit about the geometry of the surface itself can save you a lot of work. Like, is it a min? Is it a max? Oh, well, look, it's got to be a circular paraboloid, right? Therefore, it's got to either be the minimum or it's got to be the maximum. And then you can kind of tell, does it open up or does it open down? And that's how you could do it. Maybe a little more algebraically, we can say this. So if you don't know the geometry, you got to have some sort of analytical or algebraic way to figure out the same information, right? So here's one way to do it. Since we know that this is always going to be greater than or equal to 0, and this is always going to be greater than or equal to 0 because they're squares, that means that this is always going to be, I should say, the whole thing is always going to be greater than or equal to 4. And remember, 4 was the value of the function at our critical point, right? So what we're saying is, really, this is the number 4 plus a couple of positive things. So no matter what x value you plug in, or y value you plug in, or point you plug in, you're going to end up greater. So that means that this point has to be a minimum, speaking algebraically, right? This must be an absolute minimum, in fact. Okay, how about this one? So this is another one that I want you to try on your own. This one shouldn't be too bad. So try to find the extreme values of this function. y squared minus x squared. Think about it for a minute. Maybe try to imagine what the surface would look like. Okay, now say something out loud to yourself to give your brain that feedback. Right? Now work it out on your own. Try to find the extreme values if they exist. Okay, here we go. If we're trying to find extreme values, we're going to need some partials. So compute the partial with respect to x, compute the partial with respect to y, find where they zero out or where they don't exist, and this is what we got. So here's the partial with respect to x, partial with respect to y. These partials exist everywhere because they're polynomial, or they're linear, in fact. So they exist everywhere. This one will be 0 when x is 0. This one will be 0 when y is 0. So automatically, or I shouldn't say automatically, that means that our only critical point is the origin. So that is the only possible critical point. The question is it a max? Is it a min? Is it neither? Well, now we have to investigate a little bit. So if you can see what this looks like geometrically, you have your answer already. If you cannot, then we have to be a little more analytical. So here's one way to do it. If you move along the x-axis, then y has to be 0 there. So essentially look along the x-axis of our function and see what we get. So we're going to plug in 0 for y, right? And when you do that, you get negative x squared, which is always negative, right? Negative x squared will always be negative or 0, right? So if you're looking at the x-axis, you've got something that's always less than 0 or equal to 0. But maybe similarly or conversely, if you move along the y-axis, you get the opposite result. So if you move along the y-axis, you get y squared, and that's always going to be positive or 0 for all y. So as a consequence, that means there are going to be points near 0, 0 where this value is negative and points where this value is positive. So when you're near the origin, you're getting both positive and negative values. So that means that this critical point can't be a maximum and it can't be a minimum. It is a critical point, but this is actually what we call a saddle point. There's our critical point right there. Maybe I'll emphasize it right here. A saddle point. So we've seen this before. This is why we call them a saddle point, because it's, like the saddle you would throw on a horse. But as you can see, near this point, the function gets larger, but it also gets smaller. So like if you go this way, you're going to get larger values, right? But if you go this way, you're going to get smaller values. So even though this thing is a critical point, it's not a maximum or a minimum. There you go. Okay, now recall this test from Calc 1. So what we would really like is we would like a more algorithmic way, or maybe just a more certain way of determining if these critical points are maxes or mins or saddle points. Because you got to remember, the functions that you're working with might have hundreds of these points, right? Like in reality, your function could have 100 critical points and you got to test all of them. Well, you don't want to do that by hand, and you don't want to have to rely on geometry for that. You want something a little more rigorous, right? Or a little more, I guess algorithmic or procedural is a good word to use. So think about this test for a minute. Go back to Calc 1, and you might remember the first derivative test, and it said this. Suppose that you've got a critical number of a continuous function f of a single variable. That's important here. This is back in Calc 1, right? And this test was handy because it said this. If your derivative changes from positive to negative, then you have to have a local maximum. You remember doing this? If my function goes like this and then goes like that, then I've got to have a local maximum. Similarly, if the derivative changes from negative to positive, then I have to have a local minimum. So if you go down like this and then up like that, I've got to have a local minimum. And if neither of these two cases are true, then f has no local min or max at that point. So sometimes you could have this, right? Or you could have this. And that was really handy. So the first derivative test was great, and you could just you could tell immediately if you had a local min or a max. It was like a breath of relief in that particular section, right? Well, here's the thing. That test was handy when we were only working with one variable, But now, because we're working with potentially several variables, it's insufficient. There's infinitely many ways you can approach a critical point. I could approach it this way, this way, this way, this way. Things get more complicated when you have more dimensions, right? The beauty of this test was there was only one way, or maybe I'll say two ways, but really one way to approach your critical number. And it was from the left or from the right. That was it. And it was like, okay, what happens as you approach this way? It goes like that. Okay, it's got to be a maximum. Okay, what if it goes down? Okay, then it's got to be a minimum. But now, because we're dealing with surfaces and hypersurfaces and higher dimensions, we got a lot of directions to consider. So one of the things that we developed in Calc 1 was the second derivative test. I'm going to mention it here. So you might recall this, but the idea was that the second derivative gave you information about the curvature of the graph, right? So if your second derivative was negative, then your graph was concave down at that point. And if your second derivative was positive, then your graph was concave up at that point, right? So that was the idea. It was like, if you needed more information about the graph, you would take the second derivative and you get information about the curvature. Then we derived the second derivative test, and that gave you the criteria that you could use to help determine if a function is a maximum or a minimum. And there's actually a note in the book that says this test isn't really necessary in Calc 1, but that is purely because there's only one direction to approach a critical point. Yeah, so you could use it if you wanted, but you didn't have to use it, right? So just a reminder of what the test said, it said this. It said, suppose that f double prime is continuous near C. This is back from Calc 1, function of a single variable, right? If f prime of C was equal to 0, so if you had a critical point and the second derivative was negative, then you had to have a maximum. So this encapsulates the idea of, oh, hey, if you've got this horizontal behavior here, but you've also got this downward curvature, then you must have a maximum, right? Similarly, if you have a critical point, but the second derivative is positive, then you must have a local minimum at that point, kind of like this. If the second derivative was 0 or it didn't exist, then the test was inconclusive, so you had to throw it out. Now, what we want to do is we want to generalize this test to functions of several variables. And to do that, we're going to need something called the Hessian matrix. So here it is. I'm presenting it in both, in the form where it's oh my gosh, what am I trying to say? I'm going to present it both in terms of two variable functions and n variable functions, because this particular matrix turns out to be very important later on. I mean, in later classes, right? So what is it? So the Hessian matrix, or simply the Hessian, is a square matrix of the second order partial derivatives of a scalar valued function. So basically, it's a collection of the second partials, right? So if my function is two variables, then the Hessian is fxx, fxy, fyx, fyy, right? So this is the one we're going to use primarily in this section. However, the notion of the Hessian extends to any number of variables you want. So here's what it is for an n variable function. F of x1, 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 x2, x1, xn, or I should say dot, 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 x1, xn, x2, x1, x2, x2, dot, 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 x2, xn, and so on. So the Hessian is just a matrix that consists of all of your second order partial derivatives. That's it, okay? Yeah, so this particular matrix turns out to have a lot of wide-reaching implications and applications. That's why I wanted to introduce it as like a thing, okay? For one, it's used in showing that any non-degenerate critical point on a surface can be approximated arbitrarily closely by quadratic functions. So this is cool. So if you have like, a paraboloid, if you have a minimum down there, or anything that looks kind of like that, you can approximate it with a parabolic function of several variables, a quadratic function of several variables, even a saddle point. So like a saddle point, you can approximate it using quadratic functions. That's the idea. It arises when you're doing optimization problems using a Taylor polynomial, which many of you will do. That's one of the reasons you learn about Taylor series in Calculus 2, because Taylor polynomials give you a way of approximating a function. Well, the Hessian kind of lets you know if it is valid to use such a Taylor polynomial to approximate the function, right? It also lets us characterize some partial differential equations and many, many more applications, which we won't go into here, except for the one which we are going to use, which is the following test. And this is called the second derivatives test. Notice there's an S there, a second derivatives test, because we got multiple variables. So here is the statement of the test. Suppose the second partial derivatives of your function f are continuous on a disk centered at a comma b, and suppose that a comma b is a critical point of your function f. We're going to let D be the determinant of the Hessian matrix. Okay, so remember the determinant is like when you do that little swoosh multiplication thing. So we're going to take our Hessian and we're going to do the determinant of the Hessian. And when you do the determinant, you get fxx times fyy minus fxy fyx, right? And remember from, oh geez, section 14.1? No, 3? I think it was maybe 14.3. If the second order partials are continuous, then that means that the mixed partials have to be equal, right? And so since we are asserting that here, the second partials are continuous, that means by Clairaut's theorem that we can just say f of xy squared, all right? So the determinant is going to categorize the critical point as long as it's not 0. So the determinant of the Hessian gives us these possibilities. 1, if this determinant is negative, you got a saddle point. So if you go and you compute this determinant of the Hessian and you evaluate it at that point and you get something negative, you've got a saddle point at that critical point, right? Next, if you go and you evaluate it and it's a positive number and your second order partial with respect to s is positive, then that means you must have a local minimum at that point. So it's kind of like determinant is positive and this is positive, then you have a local minimum, right? This is kind of analogous to the second derivative test from Calc 1, where it's like, oh, if that thing is positive, then it's concave up, right? Yeah. The next one, if the determinant is positive and this second order partial is negative, you've got a local maximum. So now you're like this. That's what it is. And if the determinant is 0, inconclusive. You can't do anything if you know the determinant is 0. All right, now let's practice a bit. So this one, I do want you to try this one on your own. It gets a little bit algebraically complicated for a moment there. So, don't let yourself get overwhelmed. Just try to walk through carefully and we'll do it together in a minute. So think about how you would start first. All right, and then say something out loud to yourself about how you want to start. Okay, now try to work it out on your own and we will do it together in just a second. Okay, so we are looking for all the mins and max, the local mins and maxes and saddle points. We're going to need to compute some partial derivatives. We're going to need to compute the Hessian, and we're going to need to compute the determinant of the Hessian, and then evaluate a bunch of stuff. So let's do the partials first. So partial with respect to x is here. Partial with respect to y is here. Second partial with respect to x. Second partial with respect to y. And these ones are going to be the same since they're actually continuous. So if you do this with respect to y and you do this with respect to x, they're going to be equal, and you get that. So now we have all of our first and second order partial derivatives. Now we need to set them equal to 0, or sorry, set these equal to 0 to find where we even have the critical points. So here we go. If we set our partial with respect to x equal to 0, we find that y is equal to x cubed, just through some basic algebra, right? Now we're going to take this and we're going to substitute it into our other equation. So we're going to set partial with respect to y equal to 0, but we're going to replace every instance of y with x cubed. There it is. All right, x cubed cubed, and now you get this polynomial in x only. So this is where you get to factor. Factor, factor, factor. This is why we love polynomials, because you can factor them, right? Every polynomial can be factored. And if you factor over the complex numbers, you can factor them down to linear factors only. So factor, factor, factor. Here we go. X to the ninth minus x, factor out an x, boom. This is actually a difference of squares. So we can factor it as x to the fourth minus 1 times x to the fourth plus 1. There we go. This is also a difference of squares. So we're going to factor this one more time, and we get x squared minus 1, x squared plus 1. And now this is fully factored over the real numbers at least. You could continue to factor over the complex numbers, but because we're only working with real numbers, we're going to stop right here. So from this, we can find all of our critical numbers. So since this has to be equal to 0, we get that the roots of this polynomial, real roots, are -1, 0, and 1. Right here, and then right here. That's where those come from. Taking those numbers and plugging them into our original function gives us the critical points that we're looking for. -1, 1, 0, 0, and 1, 1. So those are the critical points of the function. Now we want to know, are they maxes, are they mins, are they saddle points? And this is where the determinant of the Hessian comes in. So our Hessian the determinant of the Hessian becomes this. I guess maybe I should write out the actual Hessian itself, right? So fx, oh geez, let me scroll back. 4x, I'm not going to bother with it, sorry. I'm sure you can do it yourself. As a good exercise, try to write out the Hessian for f. Remember, it's going to be fxx, fxy, fyx, fyy. There you go. So try to write that out and evaluate it at one of those critical points. Or better yet, don't evaluate it yet, because once you write out the general Hessian and then you take its determinant, you'll get this formula. So that's the formula for the determinant of the Hessian. Now we can just plug in our numbers at our critical points and see what the sign of D is. So here we go. At -1, -1, wait, was that right? Was it -1? Oops, sorry. One of these is a typo. Okay, if I plug in -1, I get 1, I get 1, 1. Can't do it in my head. 1 plus 1 plus 4 plus 1. Oh, wait, no, wait, hold on. Oh, no, I'm sorry. What am I doing? Yeah, sorry. I forgot that, yeah, see, I don't want to take all the time up with this. Shoot, one of these is a typo. I just don't know which one it is. Hold on a second. Let me pause for just a moment. All right, I'm back. Okay, so yeah, I do have a typo right here. It just kind of threw me off for a minute. To find the critical points, we were using this right here. So when x is -1, going back to this equation, y has to be -1 as well, because -1 cubed is -1. And we know that at these points, this has to be true. So we just found out that when x is -1, y also has to be -1. So this point here should be -1, -1, and I'll fix that on the slides. So this is correct. This is correct. So at the point -1, -1, the determinant of the Hessian is positive, and the second partial with respect to x is positive, so that means you must have a local minimum there. At 0, 0, the determinant of the Hessian is negative, so you got a saddle point. At 1, 1, the determinant of the Hessian is positive, and the second partial with respect to x is also positive, so you have another local minimum value right there. Okay, that's the process. Now let's take a look at a picture of the function itself, and it will make more sense why these critical points are the way they are. Here it is. So this is a graph of the function right here. And then this is the contour map with some various level curves on it, right? So what we found were that we found the 3 critical points. There's one right here, there's one right here, and there's one right here. So that's a local minimum, that's a local minimum, and that's a saddle point. And maybe if you look right here, you can see it manifesting again, right? So this is going to be a local minimum, that's going to be a local minimum, and right here we have a saddle point. There it is. Okay. All right, so now that we've got this, and now that you've kind of seen how to find these maxes and these mins, now it's time to talk about optimization problems. So, engineers, computer scientists, scientists of any kind, you're going to be doing optimization problems a lot. That's why you use this stuff, like why you care about calculus and Calc 3. You care about calculus because it lets you do this. You care about Calc 3 because it lets you do it with functions of any number of variables, right? We're going to stick to some low number variables right now, but all of this extends to higher dimensions. So let's try this one. Okay, a rectangular box without a lid is said to be made of, or it's going to be made out of 12 meters squared of cardboard. Find the maximum interior volume of the box. Okay, so if you want to try this one on your own, feel free, but at least start by thinking about how you might begin. Okay, now try to say something out loud that will suggest what you might do first to begin. Okay, and now try to work it out on your own, and we'll do it together. All right. Okay. All right, let's write down some stuff. See, the thing with optimization problems is you got to start by writing down a relationship between your variables and then trying to manipulate those relationships to get to the answer you're looking for, to get to the solution of the problem. So first thing is, let's just say the length and width and height of the box are x, y, and z respectively, just to make it agree with our coordinate axes, right? So then the volume of the box has to be x times y times z. That's our first relationship between the unknowns. Now we also have that the inner surface area of the box is 12. So computing the surface area of the box, we get this. Okay, and remember it has no lid, right? So it's an open topped box. So you get two faces that are x times y in terms of area, two faces that are y times z in terms of area, and then one face that is x times y in terms of area. This is the bottom of the box, and these are the four walls. And what we know is that the inner surface area of the box has to add up to 12. So this equation here represents a constraint that's inherent to our problem. And these types of problems are actually exactly the ones that we're going to be working with in the next section on Lagrange multipliers, because the Lagrange multipliers and the Lagrangian give you a systematic way of solving problems like this. So we have this thing, and this is a constraint. The goal with this question is to maximize the volume. So what we're really looking for is maximizing this function right here. And we need to find x, y, and z that maximize v. That's the goal here. And we have this constraint. All right, now the issue here is similar to the issue you had back in Calc 1 when you did a problem like this, which is we've got a function of three variables, and we need to find some way to get this in there. Then we need to take partial derivatives and see what kind of critical points we have, and then see if they're mins or maxes, yada, yada, yada. So first thing is this. If we solve this equation for z, we can plug the result into our formula for v. So if you solve this for z, you get this. So it's a little bit messy, but that's what you get. Now take this and plug it in for z in our volume formula, and then simplify, combine like terms, etc., and you get this. So now we have a volume formula that is only in terms of x and y. And this volume formula also incorporates our constraint already. So that constraint is built into this function. Now we're going to do partial derivatives. So partial derivative with respect to x, you're going to use the good old quotient rule. Yep, good old quotient rule. Go through some little bit of messy algebra. Remember to mind your P's and Q's. Be careful as you walk through. This is why you want to work in groups when you do these problems, because people will pick out the errors you make as you go along. But this is the partial of v with respect to x. This is the partial of v with respect to y. All right. Now, let me just pause here for a minute. You can just kind of look at this and think about it. Hopefully I don't have any errors. Okay. Now we want to see where our critical points are. So just repeating what those formulas are. Um, so when the volume is maximized, these partials will have to be zero. Now, upon inspection, just like looking at the formulas, we can immediately see that setting x and y equal to zero, that gives us a solution to that, right? So if we set these equal to zero and ask what could x and y be, well, a very basic answer is, oh, make y equal to zero, make x equal to zero, right? So that is a solution to, actually, I should say, these equations. But that doesn't make sense in the context of our question, right? So this is why context is important, and just, again, conceptual understanding is important here. X and Y can't be zero because X and Y are the length and width of the box. So if our length or width are zero, then we don't have a box anymore, and the whole problem is pointless at that point. So we toss out the solutions X equals zero and Y equals zero. That means that these things would have to be, oops, these things would have to be zero. Let me highlight them. This and this would have to be zero. And that's what I have right here. So we get a system of equations in x and y from setting these things equal to zero, just like that. Okay, now if you simplify this system, what you get is that x squared equals y squared. Notice these are the same, these are the same, and then here you're going to get x squared equals y squared. So in order for these partials to be zero, x squared has to equal y squared. All right. Now, since we know x and y both have to be positive, when we take the square root of both sides of that equation, we get that x equals y, right? So here, take the square root. X can't be negative because you can't have negative length in this reality. So x can't be negative, y can't be negative. So we immediately get that x has to be equal to y. And this makes sense if you've seen a problem like this before, that the length and the width would have to be the same. So now we can substitute this into either equation in the system that we had right here. Oof, maybe I'll clean it up again. There we go. Hey, hey, there we go. So substitute x equals y in either one of those equations, and then you end up getting this. 12 minus 3x squared equals 0. Solve that for x. Remember, x has to be positive. So then you get x equals 2. And because x is 2 and x equals y, y has to be 2. And now we can solve for z. And we get 1. There we go. So, yeah, so this is our critical point. 2, 2, 1. That's the critical point. We don't know if it's a max or a min, quote unquote, yet, or a saddle point yet, but let's talk about that right now. We could use the second derivatives test to determine if this is a max or a min, but for one, that would be very messy because remember the first partial derivatives were not exactly nice. So I would rather not have to compute another partial with respect to x and another partial with respect to y, and then another mixed partial with respect to x or y, if I didn't have to. I could use a computer to do it, and that's kind of the point, right? I would use a computer to do that. I wouldn't want to do that by hand. However, the context of the problem also immediately tells us that this must be a maximum. So we are trying to maximize the volume of a box, right? It's maximizing the volume of a box. Um, so there's no, if you wanted to minimize the volume, it would be 0. When x is equal to 0, you've minimized the volume is 0. So that doesn't make any sense. You're also not going to have a saddle point. So your only other option is that it's a maximum. It's got to be a maximum. So we have a maximum at 2, 2, 1. Those are the lengths of the sides that maximize the volume, and that gives us the maximum volume of 4 meters cubed. X times Y times Z. And that's the idea. So it's very similar to what you saw in the past. It's kind of like the same optimization technique, except now you got more variables, more variables. All right, so now let's talk about absolute minima and maxima. Kind of talked about them already, so I won't dwell too much on the definitions. A function of two variables has an absolute or a global maximum if f of a comma b is greater than all the other values of f in the domain of f. So if that is the highest mountain peak, right? And a function has a absolute or global minimum if that value at f of a, that value f of a comma b is less than every other value of f everywhere else in the domain of f. And generally speaking, absolute mins and maxes are called extreme values. So I used that phrase earlier in the lecture. Extreme values are absolute maxes and mins. That's the idea. Now, again, flashing back to Calc 1, Chapter 14 is like the Calc 1 course. It's Calc 3, but Calc 1, or Calc 1, but Calc 3. Remember the extreme value theorem. So back in Calc 1, you saw and used this theorem, and it's actually a very, very important theorem, and we'll talk about why in a minute. But here's what it said back in Calc 1. If you've got a function of one variable, suppose that f is continuous on a closed interval, then f must attain a maximum value and an absolute maximum value, and f must attain an absolute minimum value at some points in the closed interval from a to b, right? So this theorem was really important because literally it says if your function is continuous on a closed interval, then you have to have an absolute max and you have to have an absolute minimum somewhere. There's no way to escape it. So it's a very, very powerful theorem. Now what we want to do is we want to generalize this theorem to functions of multiple variables, but to do it, we're going to need a couple basic definitions from point set topology. So here we go. All right, some topological definitions. What is a closed set? So when we talk about a closed set, what does that mean? A closed set is a set that contains all of its boundary points. That's what a closed set is. Okay, so then what the heck is a boundary point? Well, that's this definition. So what is a boundary point? A boundary point of a set D is a point P such that any open ball with center P will contain points in D and points outside of D. So this is one that I want you to look at for just a minute and think about what a boundary point is. And I'll show you some pictures in a moment. Maybe even like read it out loud to yourself a couple of times. Okay, so basically a boundary point is any point where if I put a little open ball around it, the ball will reach outside of the set and inside of the set. That's a boundary point. Yeah, for any open ball, any open ball. So not just one, but any possible open ball that I put around that point is going to reach inside and outside the set. So here's an example. Let's just look at the plane R2, and let's look at this set D. So this set D is this one right here. Maybe think about what you think this could be in the plane. So we're not in three-dimensional space right now, we're in two-dimensional space. It's the set of all points here, and this is the set of points that are inside the closed unit circle. Oops, double right here. Yeah, so these are the points that are inside and on the unit circle x squared plus y squared equals 1. And x squared plus y squared equals 1 is the unit circle itself. So the unit circle itself is the set of boundary points. It's the boundary of D. So pictorially speaking, it's like here. Here's the origin. The radius is 1. So what we're saying is that D is this entire set, the inside of that disk, and the boundary itself, the circle itself. That's D. So this set is closed because the boundary points of this set are all on the circle itself. So the boundary points are all of these guys right here, right? Those are the boundary points. And if you pick any one of those points on the boundary circle and you make an open disk centered at that point, your open disk is going to reach inside and outside the circle. See that? The little circles that I'm drawing are reaching inside and outside. That's why these are all boundary points. So that's how you define a boundary point. Here's another example. So two other closed sets in R2. You've got a circle, you've got a square. Notice, again, if I pick any point on the boundary, and I draw a circle around it, the circle reaches outside and inside. That's how you define a boundary point. Now, similarly, but very different, there are sets that are not closed. So if you remove even one boundary point from the set is no longer closed. That's an important detail here. If you remove even one, you no longer have a closed set. Okay, you got to have all of the boundary points. So here are some examples of sets that are not closed. Here we go. So this one is definitely not closed. This is basically the open unit disk or the open disk. It doesn't include the boundary, so it can't be closed. If it's not including the boundary at all, it can't be a closed set. Here is also a set that is not closed because what's happened is we've taken this boundary point and removed it from the set. Well, now it's like I don't want to say this, we not closed the set. I don't want to say open because just because a set is not closed does not mean that it is open. So it's not like a door in that sense where if it's not closed, it's open, right? It's not like that. Topology can be weird in that way, but this is a set that is just not closed. It's just not closed. Why? Well, look, if this is a boundary point, that's a boundary point. Why is it a boundary point? Because if I pick it and I draw a little circle around it, it contains points inside and outside. So we removed a boundary point, now it's no longer closed. Over here, this example, this picture, is very much not closed. It's a square and it's got one of the sides included, but the other sides are not. So it's not closed, right? Now, this leads us to a very important definition we're going to get to in a second here, called compactness. So before we can talk about compactness, we need one more definition. What is boundedness? So a bounded set in Rn is a set that can be contained in a ball of some finite radius. So in other words, when we talk about a bounded set, we mean a set that doesn't just expand out forever. So bounded means I can bound it. And what do we mean by bounded? It means I can put it inside of a ball. If I can't put my set inside of a ball with finite radius, it's not a bounded set. It's reaching out to infinity in some way. So not bounded. Now, the big definition here is compact. So what is a compact set? A compact set is a set that is both closed and bounded. Okay, that's the good one. We want sets that are closed, meaning including all of its boundary points, and we want it to be bounded. So if you satisfy both of those conditions, your set is called compact. All right? Okay. Yeah, if you want to read about compactness, please, you're welcome to go down that rabbit hole. Compactness is an incredibly useful property for a set or a space to have. Compactness basically guarantees that nice properties of other mathematical objects have to hold true. So if you've got compactness, you've got something really, really nice. Here is a very important example. I use this result in my own research, and this result basically gives us the theorem that we're about to talk about. So here's an example. Continuous images of compact sets are compact. It's a simple statement, but what it means is if the domain of a continuous function is compact, then so is the range. So if you've got a continuous function defined on a closed and bounded set, then the range of that function must also be closed and bounded, which is a powerful result. It's like forcing something to be true, this compactness and continuity. Intuitively, compactness is like the next best thing to finiteness. So for example, these things here, both of these sets are compact, right? They're closed because they hold all their boundary points, and they're finite in extent, so they're bounded. So both of these sets are compact sets. And what you'll notice here is that it's not that these sets are okay, I'll say it this way. These sets contain an infinite number of points. There's an infinity of points in here, right? There's an infinity of points in there, but they're all contained in a little disk, and we're including all the boundary points of the disk. So that's compactness. It's like the next best thing to finiteness. If you can't have finiteness of like, cardinality, I'll say, but you can like cluster everything and it's closed and it's bounded, you're pretty good. You're pretty good. Okay. So in this course, why do we care about this? In this course, compactness of a set and continuity of a function give us the following theorem, which is the extreme value theorem. So The extreme value theorem for multivariable functions says this: if f is a continuous function defined on a compact set D in our n-dimensional space, then f must attain a maximum value and it must attain a minimum value at some points in the domain of the function D, the domain of the function f. Yes, so just like I said before for single variable functions, if your function is continuous on a compact set, then you must achieve a maximum value and you must achieve a minimum value, that function. That's the big idea. Okay, so this is another one where I want you to stare at it and just think about it for a minute. And then we'll finish up with basically a lengthy example. Okay. All right. Oh yeah, so first, little note. Oh, now we're going to talk about absolute maxes and mins. Little note, if f has an extreme value at a point, then that point is either a critical point or it is a boundary point. Those are the two cases. And just as a little side note, a tangential note, one nice property of harmonic functions, remember the ones we talked about before, they actually have to achieve their extreme values on the boundary of their domain. So that's a nice property of harmonic functions. If you find an extreme value, it must be on the boundary. Okay, so what we would like to do is we want to be able to determine absolute maxes and mins of continuous functions on compact sets. So how do we do it? We do this process right here. First, find the values of f at all the critical points in the set D. So like the interior, the inside of D. Then find the extreme values of f on the boundary of D. So you're breaking it into two cases. What's going on the inside and what's going on the boundary. Then the largest of the values is the absolute maximum, and the smallest of the values is the absolute minimum. All right? Okay, here we go. Find the absolute maximum and minimum values of the function here on this rectangle in the plane. And for this one, what I want you to do is, well, think about it for a minute. Just think about what it's asking. Then I want you to say out loud what you might start with. Like, what do you think you need to do first? Okay, and now what I want you to try is I want you to try to find the local minimum and maximum values of the function the same way that we did before, and then we're going to look at what to do on the boundary. Right, okay, here we go. So absolute mins and maxes. So I need to find all the critical points inside this rectangle first, and then we're going to look at the rectangle itself and figure out what our function is doing on the rectangle, the boundary of the rectangle, sorry. Okay, so here they are again. Oh yeah, first thing to note is that this set is indeed closed and it is bounded, therefore it's compact. That's a good thing. Secondly, this function here is a polynomial, and remember polynomials are continuous everywhere on the plane, so we've got a continuous function defined on a compact set D, therefore by the extreme value theorem, we know that it must achieve an absolute maximum and it must achieve an absolute minimum. That's what we've got here. So now we need to find the critical points. Do the partial derivatives, set them equal to 0, find the critical points. So partial derivative here, partial derivative here. These exist everywhere, so our only critical points occur when these are equal to 0. When we solve these equations, we get that there is only one critical point inside the rectangle, and it's 1, 1. What is the value of our function at that point? 1. There we go. So what we just found was we found a critical point inside. Now here is where things are going to get a little bit tedious. So let's go. What we need to do next is we need to find the extrema that are on the boundary of D. So basically on the actual bounding rectangle. That's what we need to do next. The way we do this is we decompose the boundary into 4 separate line segments and then analyze the function on each one of those line segments. So we're going to focus on just L1, see what's going on that line, focus on L2, see what's going on that line. Focus on L3, see what's going on that line, and then focus on L4 and see what's going on that line. So tedious, but here, we're going to do it. All right. So on L1, so we're going to do this first. On this line, notice that the y coordinate is always 0 on this line. So we can adjust our function in that way. So this becomes this, which is just x squared, and x is going between 0 and 3. Let me flash back for just a moment here. So y coordinate is 0 here, x goes between 0 and 3, and this is what our function looks like on that line, which is just the good old x squared parabola. Easy, right? So x squared is an increasing function as x goes from 0 to 3. So because it is increasing, that means it achieves its maximum at the point 3, 0. Plug that into our function, we get f of 3, 0 is 9. It also has to attain a minimum value over here, so we plug that into our function and we get 0. So on L1, we have these two potential candidates for a maximum and a minimum value of our function f. Right? So let me pause for a minute here. Think about what we just did before we go do the other lines. Oops. Okay, now let's move on to line 2. So on line 2, just a reminder, it's this one right here. On line 2, x is equal to 3. And then y is going to vary between 0 and 2. So on L2, this is what our function looks like. Plug in 3 for x, our function simplifies to this, and y goes between 0 and 2. Kind of a similar argument as before. This is a linear function, but it's got negative slope, so it's going to be decreasing as y goes from 0 to 2. So because it's a decreasing function, that means it achieves its maximum when y is 0, and its minimum when y is 2. So when y is 0, and x is fixed at 3, we have f of 3, 0 is 9. When y is 2 and x is equal to 3, we get f of 3, 2 is 1. All right, now we've collected that data. Now let's move on to line 3. So just a quick flash back. Line 3 is this one. On line 3, the y value is fixed at 2, and x goes from 0 to 3. So this is what our function looks like. We're going to fix y at 2, plug that in, simplify this, and we end up getting this as our function, which simplifies to this shifted parabola on this interval. Okay, so I think now you've kind of got the idea of what you have to do, right? So analyze this function on this interval and find the maximum and the minimum. That's all you got to do. So it's got a minimum value here at 0. It's got a maximum value here of 4. Then we go on to the next line. Now I'm just going to jump right to it. So lastly, on the last line, x is equal to 0, so our function becomes 2y. Again, it's linear, it's increasing. Its maximum value is achieved at 2, and you get 4. Its minimum value is achieved at 0, you get 0. Okay, now we've found all the possible candidates for the absolute maximum and minimum. So comparing all of these extreme values on the boundary, the minimum value on the boundary is 0, and the maximum value on the boundary is 9. Then if you compare that to our local maximum that we found inside, or minimum, just some local point. Actually, let me be sure, 1, 1, yeah, I don't actually, it's not a max or a min, so I gotta fix that too. Shouldn't say that, I should just say a critical number, or critical point. But the number we got there was 1. So that's not less than 0, and it's not greater than 9. So now we can conclude that the absolute minimum value of our function on the rectangle D is 0, and the absolute maximum of our function on the rectangle D is 9. And it just happens to be the case that they both occur on the boundary. So you can kind of see it in this picture. This is what our function looks like when you restrict it to that rectangle. And you can see here's the minimum, and here's the maximum. And that's what you got right there. Whew, man. Okay. And on that note, let's play. um, Let me make one last comment and then I'll stop the recording here. As you can see, this is very, very tedious. This is very tedious, and you don't really want to have to do all of this by hand, right? So this is a good point to think about and just like let the idea of a human's job versus a computer's job really settle into your brain and realize, I don't want to have to do this. This is something that I would hope a computer could do. If there is some algorithmic way we can tell a computer to do this, I would prefer that. Keep that thought in mind, okay? But on that note, let's play. Um, Tried to keep it as short as I could. So thank you again for listening, and I'll see you all next time.